So we were, let's see, where were we? Yeah, so we finished the theorem 12.4, right? I think, is that correct? You finished or not? All the statements of, I mean, there is such, theorem 12.4 had 3 statements. Yes. We went through all of that. Right? Okay. So now we go to the next one. Right. Okay, yeah, so the conclusion from the theorem, previous theorem was that the general structure was, or the Lie algebra was, that the kappa, so Hi, Hj, of course, this is 0, where Hi and Hj belong to the kappa subspace, and then Hi with x alpha, these are the roots, non-zero roots. This was alpha Hi, x alpha, so where alpha belongs to delta and Hi belongs to, Hi is understood that belongs to the kappa. And x alpha, x beta, now this was, there are several possibilities. So this was, so if alpha plus beta is equal to 0, which means beta is equal to minus alpha, then it was b x alpha, x minus alpha, h alpha. Now if alpha plus beta did not belong to the roots, then, I mean, so alpha plus beta, so this is alpha plus beta equal to 0, and the other two cases are alpha plus beta not equal to 0. And then here we have 2 possibilities. One, alpha plus beta belongs to delta, does not belong to delta, then it is 0. And if alpha plus beta belongs to delta, then if it is not 0, it is going to be x of alpha plus beta, right? With some coefficient, right? But now the question is, of course, in SU3 we know this is not 0, right? Remember, take alpha 1 and alpha 2, x alpha 1 and alpha 2, alpha 1 plus alpha 2, right? Remember, in SU3 case, we had x alpha 1, remember the roots were this, alpha 1, alpha 2, and alpha 3 was here, right? So x alpha 1, x alpha 2, we know, because alpha 1 plus alpha 2 is equal to alpha 3, so it is going to be proportional to x alpha 3, right? But the question is, what is that number? Okay. Whether that number could be 0 or not. If the number is not 0, you can always normalize them. It's not important, that part. Main issue is whether the number is 0 or not. And we saw that the number was not 0. It was some non-zero quantity. Right? So the question is it a general statement? I mean, does it happen generally or not? So one would like to figure out, to understand whether is it possible that an alpha beta could be 0. So these are the kind of main things about, and several other points we want. So next theorem is going to address that issue, plus some other things. So 12.5, theorem 12.5. So now we have already used this method already in the previous theorem, the point number 2. We use this chain or string, it's called a string. This is a definition, alpha string through beta. Beta consists of beta plus alpha, or beta minus alpha, all the way up to, okay, so let me just write like that, beta plus n alpha. set where n belongs to integers. N belongs to integers. So this is just a definition. This is called alpha string through beta. So the picture of that was, I mean, if you think of this picture, so let's say I have some alpha, okay, and some beta, we don't know, some beta. Then what I do is I just look at beta plus alpha. So this is beta plus alpha, beta plus 2 alpha, and so on, right? And beta minus alpha, and so on. Just look at all this chain. And the reason why we are looking at this chain is clear, right? Because we have already seen that for every alpha, there's an SU2 subalgebra, right? X alpha, so for alpha there's an SU2 subalgebra which consists of X plus minus alpha and H alpha, right? This defines an SU2 subalgebra. So what one is looking at here is the representation of this SU2 subalgebra. So whatever it is, I mean, when I apply these generators, these three generators, it is just going to, when H alpha acts, of course it will stay there, right? Because Cartan, it's just some, these are eigenstates of the Cartan subalgebra. But when X plus or minus alpha act, you're just going to move along this line, right? So this chain, I mean this string, will be in some representation of SU2 subalgebra. Okay? And now we are going to study this SU2 subalgebra and get various conclusions from this. Okay, so now, I mean, first of all, we don't even know at this stage. Maybe let's say, for example, these two exist among the roots, and then maybe this one doesn't exist, that one doesn't exist, but the successive, these ones exist. Who knows, right? We don't know anything about it so far, right? So let us consider a string which consists of consecutive elements. So nothing is missing. Okay. So let's think about the following. Then let's consider a string which starts from so let's say I consider this string which starts from beta plus n equal to r to n equal to s. So we are saying that, let us say that I have, so beta plus n alpha is some point here, beta plus r alpha, and then there is a consecutive string, so beta plus r plus 1 alpha, beta plus r plus 2 alpha, all of them, and all the way up to beta plus s alpha. So what we are saying is that we are considering a consecutive string where each one of them is a root. Okay? So we consider that.
This sum can also include negative values.
Huh?
This sum can also include negative values for
well, I mean, I could have chosen r equal to some negative number. Doesn't matter. Huh? But what is important is that for every integer between r and s, this is a root. Beta plus n alpha is a root. So it's some consecutive. Okay. Okay. So now we again. So same trick. The standard trick all the time we use to take trace of h alpha in this space. Let's call this space V. We take the trace of h alpha in this thing, and again this should be 0 for the same reason that we have always been saying, right? Because this h alpha, I can write it as a commutator of x alpha with x minus alpha. I mean, I should really put here add h alpha. So this is again add h alpha, x alpha. Okay. So for the same, so then this commutator for the cyclicity property, which we have used many times, right? So this must be 0. Right? It is because you see that what we are saying is that this is a consecutive chain. Previous one is not existing. The next one is not existing as a root, right? So then this will be a subspace. This B will be closed under the action of this SU2 subalgebra. It will be closed, right? Because H alpha will keep you at the same point. X plus alpha will move you across here. But when it acts here, it vanishes because there is no root there, right? And X minus alpha will move you backwards, one step to the left, right? But when it acts here, there's no other point to go to because it's not a root. Huh? So this consecutive set will form a subspace, a closed space on which this SU2 acts. So therefore, I can use this cyclicity property, and that's okay. But then we can directly compute it. So what is the result? So this is the same as beta plus n alpha h alpha, right? I mean, so let me write it two steps. This is the same as sum over add h alpha acting on g beta plus n alpha, right? And n going from R to S. So which is the same as beta plus n alpha h alpha summed n equal to R to S. Yeah, we have already proven that the dimension of each, I mean, I don't have to, normally I would put also the dimension, but we have already proven in the previous theorem that the dimension of each of these spaces is 1. Huh? So it's just that. Okay, so what is this? Well, this is the same as, so beta of h alpha and summed. So this sum is what? S minus R plus 1, right? I mean, here there is no n appearing in the first term, beta h alpha. And then you have alpha h alpha times summed over n going from n equal to R to S. I mean, here it was a sum, the same thing, but sum 1, n equal to R to S. But this sum is simply S minus, how many times this appears, right? So the number of times it's going to appear is S minus R plus 1. Right? Whereas this sum will become S minus R plus 1 times S minus R. This is the usual summation over n. No? This, I think everybody is familiar with that, right? Okay. So combining the two terms.
Over 2.
Eh?
Over 2.
Eh?
Over 2.
Over 2, sorry, correct. Thanks. So combining the two terms, we find that 0 is equal to S minus R plus 1. Right? That's a common factor. And you find here beta of H alpha plus S plus R by 2 alpha H alpha. That should be equal to 0. That's equal to 0. Now this is certainly not 0. Right? Because clearly, I mean, in this thing, S is greater than or equal to R, right? So S minus R is something non-negative, and then I have a 1 here, so this is certainly not 0. So the only way this can be 0 is if this is 0, right? So we can get an equation from this. So this implies 2, well, beta H alpha was nothing else but beta B of H alpha H beta, right? Divided by this one, which is B, H alpha, that's equal to minus S plus R. Huh?
S minus R, not S plus. S minus
R. S minus R. S minus R. S minus R, correct. S minus R. Yeah. No. Sorry, no, this is S plus R. No, that should be S plus R. I mean, the one way to do this is the following. Okay, let's try to do this. you can separate the sum. Okay, let's call n. I mean, here I think we are familiar with the n equal to 1 to something, or n equal to 0 to something, right? So then there will be a, please, I mean, you can check it. It should be plus r.
Because we need s square minus r square in the sum. So that's why.
Correct.
Yeah.
That's plus r. Should we try it, or you can check it? Okay. So it should be plus r. Okay. So this is very interesting, right? So what it is saying is that this has to be some integer. This ratio has to be some integer. Already there's something interesting appearing here. Okay. Also, this tells you something else. That in fact, the picture that we were drawing, remember that the beta here, and then this was some beta plus r alpha up to beta plus s alpha. Beta plus s alpha. This was, we said, one consecutive, right? Perhaps there could be another consecutive, maybe, no? But this tells me that there cannot be any other consecutive. This is the only consecutive one, right? Because suppose there was another one, let's say from r prime, beta plus r prime alpha to beta plus s prime alpha. So suppose there was another consecutive chain, such that the previous one is not a root and the negative one is next one is not a root, because that we needed to use to say that this was an invariant space, right? So if that is the case, then you see we'll find again, you can do the same calculation again, then we'll find that this is equal to minus s prime plus r prime. Okay. So now suppose, I mean, okay, so these two things have to be equal. So then, I mean, suppose s prime is greater than s. Okay. There are two, I mean, one of them, if they are not equal, one of them will be greater than the other, right? So let's suppose s prime is greater than s. No, see what I'm saying? Suppose there's another consecutive chain. Then you go through the same analysis, but now with the r prime and s prime. Okay. Then we will get the conclusion that this quantity, the same quantity, is equal to this. So these two must be equal, right? So now the two possibilities, say s is equal to s prime. Okay. If s is equal to s prime, then r is also equal to r prime. Then we have nothing else. I mean, it's the same consequence. This is not different. It's the same as that. So let's suppose if they're different, suppose s is different from s prime, then one of them should be greater, right? So let's suppose s prime is greater than s. Then r is less than r prime.
This is contained in the diploma.
Then r prime will be less than r. So then what would it mean? So s prime, we are saying s prime is greater than s. So somewhere s prime is sitting somewhere here. Okay. And r prime is less than r, so r prime is sitting somewhere there. Then this chain includes that this string will include that string, right? But that's not possible because we already said that for the previous thing, s plus 1 was not existing, right? Yeah? So therefore we see that there is only one chain, there is only one string. Starting from, there is only one alpha string through beta, a consecutive string. There's nothing else in this string. That's one statement. Is that point clear? I mean, because this would imply that this range is actually overlapping that range, bigger than that range. It includes that range. But by assumption, we already said that if s of b beta plus s alpha is a root and beta plus s plus 1 alpha is not a root. So that's not possible, right? So it should be the same thing.
But originally you choose S and L.
Sorry?
You choose S and L. So the result should be the same for any range that you choose at the beginning. For any B space, it shows n equal to different R to a different S, and I will get the same result. for any.
Could you repeat that again? So we are talking about the alpha string through beta, right?
Yes.
Yeah.
We choose a very particular R and a very particular S, but I could have chosen any other, and I should get the same result because the analysis doesn't depend on.
No. I mean, it is important to use this formula. I mean, to show that this is 0. What we want is that. So in the previous thing, beta plus R minus 1 alpha is not a root. And similarly, beta plus S plus 1 alpha, S plus 1 alpha is not a root. Because otherwise, this space would not be closed under the action of X alpha, X minus alpha, and H alpha, right? We need to use that. Otherwise, this we cannot use this. It will not be 0 in general, right? So that is the point. So it's not just arbitrary R alpha, R and S. It is something such that the previous one does not exist and the next one doesn't exist.
So we can now see that the plus sign was very crucial here. If it was minus, then we could have any other conjective root because we can choose any two numbers whose difference is the given number. Because if it was S minus R, then you could choose any two numbers.
Correct. Yeah. Sure. Absolutely, yeah. So please check this. I mean, if you can. I think you can just. The easiest way to write it. This is important. S plus R, right? So the easiest way to write it is write n is equal to some m plus r. No. Then this sum. So this sum becomes. So write n equal to m plus r. So initially the sum was r to s n, but then this is the same as m plus r to s. Okay, and the range we said when n is equal to r, n is 0. So what is the sum of? So this is. I mean, sorry. This I will just substitute that. But now I want to tell. I want to say what is the range of n, right? You see, the range of n was the minimum value was r. So when n is equal to r, n is 0, and when n equal to s, n will be s minus r. So the range is here 0 to s minus r. Okay. So let's do that. So this becomes the first term m sum over n. So m equal to 0 to s minus r. So that gives me s minus r times s minus r plus 1 by 2. Right? The first one. But the second one gives me r times s minus r. Right? S minus r plus 1. Yeah. Okay. So now you add the two things up. So s minus r plus 1 is a common factor. Take 2 also. Then you get here s minus r plus 2r. And that makes sense. That flips the sign. Huh? So it was crucial. That sign was crucial. Yeah.
So part of the argument in this case would be that the metric is not degenerate, right? Because of the condition for B H alpha is alpha.
Yeah.
If this wasn't the case, like in
Precisely. So that we have already used for the previous theorem, right?
Yeah. This is only applicable for semi-synchronous algebras.
Yeah, correct. Yeah, sure. Yeah. Okay, so then, so this is the conclusion. So there is only one range, right? But we already assume that beta exists, right? So R better be a negative integer, right? I mean, if R was positive, then, I mean, and S is also, of course, S is greater than R. So this whole thing is outside beta. Beta will not be part of it, right? But we said there is only one string. Right? So beta must be inside this string, which means R must be a negative number. So the conclusion is, so what we are saying, so from this, what is the conclusion? That the alpha string through beta it goes like beta minus, say, let's call it now P alpha all the way up to beta plus Q alpha, where P and Q are non-negative integers. So really beta is inside it in this string. And it's a consecutive string, which means that element exists here. Every element is part of the roots. Okay. And furthermore, we get this important result that by substituting r is equal to minus p, you see that 2b h alpha h beta divided by b h alpha is equal to p minus q. So we are taking s to be q and r equal to minus p, right? So there is a q and minus p which are combined. This is quite amazing, right? I mean, so we are beginning to see that. I mean, think of this as like dot products. I mean, the inner products between the h alpha h beta. That these are this ratio is going to be integer of this. This is already quite amazing, right? Okay. Okay, then I go to the next point. But is there any question here in this proof?
What's the beta should be included in the string?
Because we already said that alpha and beta are two roots which exist, right? So alpha, yeah, the starting point is that we are saying alpha and beta belong to delta. So beta certainly is a root, right? Now, suppose that this string r was positive, right? Then beta is not part of this string, right? But that's not possible because we said the previous proof was showing that there is only one string, one consecutive string, right? Otherwise, there would have been another consecutive string from here, which is in contradiction with that statement. Any other questions? I mean, think about it. Maybe let's take a few seconds of break.
This does not limit the possibility that there might be another string with other two roots.
Repeat that again.
And there could still be another string between two roots, another consecutive string.
Yeah, we could have another root gamma, which is not part of this string, and from there again there will be alpha string through gamma, right? Yeah, that's certainly. Again, in the SU3 case, so if I take the alpha 1 string through alpha 2, then it will be just these two, right? But then if you take from minus alpha 3, there is another string, right? Alpha 1 string. So minus alpha 3 and minus alpha 2. Right, that will be. Yeah. Okay. Now the next statement is okay. The next statement is, you see, we already proved before, in the previous theorem we proved one statement, which was that, the first the theorem 12.4 and point 3, the third point, that is dim G alpha was equal to 1 and G n alpha is empty except n equal to 0 or plus minus 1. This we had proved before, right, in the previous theorem. Now we will say, so this tells you that, if alpha exists, then 2 alpha does not exist, or 3 alpha does not exist, minus 2 alpha. But it doesn't say anything about, what about some fractional number? Maybe if alpha exists, but perhaps, some other points, some even irrational number, pi times alpha. How do I know pi times alpha does not exist? No. So now we will. So the next point of this theorem is actually that there is nothing else. No number times alpha exists apart from 0, plus, and minus 1. Okay, and so that is basically using this result. So let's suppose, so now we take beta to be some c times alpha, right? So we want to check. We want to say that the only time this could be a root is if c is equal to 0 plus or minus 1, right? Nothing else. 0 is of course a trivial. 0 is the Cartan part, but a non-zero thing can be only plus or minus 1. That's what we want to prove. At the moment, I'm just saying that this could be any number. Beta is any number times alpha. So if you do that, then let's look at the left-hand side. It will be, remember, h beta was defined like what? It was beta of h was equal to b of h beta h, right? For all h. This was a definition of h beta, right? This was a map which from the dual space to the original space, right? That was a map. But now if I multiply this by c, then what's going to happen? If beta is c times alpha, if beta is c times alpha, that is the same as b times c h alpha h, right? Because this is linear. B is a linear thing, right? And bilinear in each of these. So, or another, yeah. We said alpha h is that. Alpha h is that. Now, what is c times that? This is a definition, right? This is a definition of h alpha. But c times that is simply c times this. Right? But then I can multiply the c inside. Right? Then this implies that the c alpha is, c h alpha. So that h beta therefore is c of h alpha. That's what they're saying. If beta is equal to c alpha, then h beta is c times h alpha. So then I substitute that here. So what we get here is 2 times c times b h alpha divided by the same quantity. So this cancels, your numerator and denominator. So 2c is equal to p minus q. Right? So 2c, so conclusion is 2c is an integer. Okay. Okay. So yeah, conclusion is that 2c is an integer. Okay. So at the moment what we did, so we are saying that beta is equal to c alpha, and we consider the alpha chain through beta. Alpha chain passing through, alpha string passing through beta. But I could have done other way around also, right? I could have considered beta string through alpha, right? So what will I get in that case? So this was the conclusion we obtained by considering alpha string through beta. Okay. But now let's consider beta string through alpha. In that case, what am I going to get? I'm going to get 2 b h beta h alpha divided by b h beta. Right? Now we just exchange the role of alpha and beta, and this is going to be some other integers. Who knows what? But whatever it is, some integers, p prime minus q prime, right? But whatever it is, it's going to be some integer. So now again, substitute h beta is equal to c h alpha. Then the left hand side. So I'm substituting now h beta equal to c h alpha. Substituting that, here numerator you get a c, denominator you get c square. Right? So you'll get here 2 over c. Okay. So the conclusion is not only 2c is integer, but 2 divided by c is also an integer. It's a very tight structure, because the point is that every root defines an SU2, right? Just like, for the alpha string through beta, what we did, we used the SU2 coming from alpha, right? Now for this beta string through alpha, we are using the SU2 coming from beta. And that's the point. I mean, it's so tight structure. That's the reason why we are getting this strong conditions. So 2c is an integer and 2 by c is an integer. So the only possibility for c is equal to 0 plus minus half plus minus 1 and what is it? And plus minus 2. That's it. There are no other possibilities. Right? I mean, for example, 3/2 is okay for that, right? That condition is okay. But then if you do this, this becomes 4/3, right? That's not an integer.
But 2/0 is
For the 0, okay, 0 is a trivial case, right? I mean, there is no, yeah, nothing. Yeah. Anyway, yeah, exactly. For 0, we cannot say anything. Yeah. Okay. So now let's see what are the possibilities here. So we can exclude this already, right? Because this remember, this is so what it is beta. Therefore, if I choose this is plus minus 2 alpha. But this we have already excluded from that previous theorem. That if alpha is a root, any integer n which is not equal to 1 or 0 is not a root. So this is not possible. Okay. What about this? Well, if this was the case, then you see alpha would have been, so for this case, so if I take, so this was for the case plus minus 2. For if I take plus or minus half, then alpha is equal to plus or minus 2 beta. Right? But that's again excluded. So this also goes out, and that's it. Right? So, so it's quite amazing. I mean, how tight the structure is. I mean, okay. Now the last statement of this theorem. Right. So now the last statement of the theorem is the thing that we were mentioning before, right? That if I have the commutator x, I mean, if I look at x alpha, x beta commutator, and let's assume that alpha plus beta is a root, is a non-zero root, and alpha plus beta is not equal to 0. Okay. So alpha plus beta is a non-zero root. It exists as a root. Then we were saying that generally we know it should be something like this, right? But the question is whether this could be a 0 or not. So what this third part is going to prove is that this cannot be 0. So the proof is by contradiction. So let's assume it is 0. Okay. So proof. So we want to prove. So what we want to prove is n alpha beta is not equal to 0. This is what we want to prove. Right? So start by assuming that the contrary, and then prove that there is a contradiction. Okay. So the idea is the following. Suppose n alpha beta is 0. Then you can consider a chain, it's alpha string, but of this type. I mean, so we start from. So let's just write this. So anyway, I mean, even before doing this, already from the previous statements, we already know that this quantity which is 2b h alpha h beta over b h alpha h alpha is equal to p minus q. Okay, where what were the p and q? So this was the string which was going from beta minus p alpha all the way up to beta plus q alpha. Right? This was a consecutive string. Right? But now, if this is 0, you see, and remember how we did that. We considered the space of all this. We considered the sum of all these spaces, G beta plus, say, n alpha, where n goes from minus p to q, right? Okay, and this was indeed, since there was nothing else on this side and that side, this was a closed space under the action of x alpha, x minus alpha, and h alpha, right? But now, if this is true, then you see you can make a smaller space. Here you get a beta. Beta is somewhere in between, right? If this is true, then actually you could have just considered this space, right? Because what will happen? I mean, x minus alpha pushes you back, right? This way. X minus alpha will go one step at a time to the left. X minus alpha anyway annihilates it because there is nothing, no root existing on that side. Here, even though a root exists, beta plus alpha does exist because we are assuming that beta plus alpha belongs to the root. But if this is 0, if that commutator is 0, then you see x alpha annihilates it, right? So I can consider a smaller space in which I take the trace, right? But if I do that, so that means we are saying, so let's consider the space now. The original space was that, right? Which we used to prove this. But now I consider a smaller space, V prime, which is simply sum n equal to minus p to 0 of g beta plus n alpha. Whereas under this assumption, this also is closed. Huh? Is that point clear? I mean, if so, then I can take again the same argument, trace of h alpha in this space, in the V prime, should be equal to 0, because this is a closed space, and this is a commutator of x alpha with x minus alpha. So it vanishes. And now this left-hand side is going to be beta plus n alpha acting on h alpha, summed, n going from minus p to 0. Okay. So, I mean, you get, this is exactly the type of thing that we did to get this expression, except that at that point, this upper limit was q, right? So, from this analysis, we'll find that 2b h alpha h beta over b h alpha is equal to p, because here this is the same calculation which led to this result, except that upper limit was q. But now upper limit is q, 0. So just substituting q equal to 0. Correct. So now we have the two equations for the same quantity. Left hand side is the same. So right hand side better be the same. So q must be 0 then. But q cannot be 0 because we are saying that alpha plus beta is a root. So q is certainly greater than or equal to 1, right? So that is a contradiction. So this cannot be true. Right? So this must be, n alpha beta must be not 0. This must be 0. Okay. I mean, let's wait for a few seconds. I mean, think about it. Any question, any doubts? Yeah, so these two equations together imply that q equal to 0, but that's a contradiction. Because if q is equal to 0, alpha, if this would imply that alpha plus beta is not a root. But that's a contradiction. Okay, now with all this, now we can actually really talk about subspace of the. You remember we had complexified everything. All the Lie algebra is complexified. So we are allowing complex number multiplication by complex numbers, right? But now what we can do is we can take this complex Cartan subalgebra, and go down to a real subspace where the metric is completely positive. Cartan killing form is positive. That was because remember yesterday I think when we proved at one point that B H alpha is not 0, right? Somewhere one of the statement was that, no? That B H alpha in the previous theorem 12.4, one of the statement was B H alpha is not 0. That was, I mean, kind of looked obvious, right? I mean, from our experience with the real vector spaces, it was kind of obvious. But even for the real vector space, it's not really obvious, right? Because remember, take the Minkowski space, right? There are null vectors, right? Everything is real, but metric is has some signs are negative, so it's not a positive definite metric, and that is why you have light-like directions, which are null. So even in the real spaces, it may not be. I mean, norm of some vector could be 0 if the metric is not positive definite. Right? So now the statement is that we can actually find a subspace in this Cartan subalgebra where the metric is positive definite. Okay. In which case, of course, there will be no such possibility. So the idea is the following. Right. So. There. So the statement is, if I take H alphas, H alpha of course span the entire space, right? When I take all the possible alphas, H alpha, all the possible, so alpha belongs to delta, alpha are all the elements of delta. Then I mean, when you include all of them, it spans. I mean, spans the full space, full Cartan subspace. So far, we were allowing, so we were writing any H as some complex number, C alpha, H alpha, summed over alpha, right? I could write it. Of course, this is over, I mean, it's not the basis really. There are too many. I mean, like in the SU3 case, there were 6 roots, right? But the space was only 2-dimensional. It doesn't matter, it's overcounting, but it doesn't matter. I can consider all the sum of all of these guys, but with complex coefficients. It's overcounting, doesn't matter. That's not a problem. This is certainly a part of the Cartan subalgebra. But now what we'll do is consider this. So this was the generic element of the H that so far we were talking about, the Cartan subalgebra. Okay. Now we'll define an HR. Okay, this is just a notation, which will be kind of a subspace of this, where what you do is you just restrict these numbers to be real. So let's say R alpha, H alpha. So here these were complex, and here I'm going to just restrict myself to the real numbers. And the claim is that this space the Cartan killing form on this subspace is positive definite. So how do we prove this? I mean, it's very important to do that, because once you have a positive definite space, then because we understand positive definite space, geometrically we can visualize very easily, right? So all the standard Euclidean geometry things, trigonometric rules and things like that we can use. Huh? So so that's quite important too. Then this space is positive definite. So B restricted to HR is positive definite. That is the statement. So the way to prove it is, You remember this formula, which I think long time back we had put. It was part of the exercise problem actually, right? One of the exercise problem was that if I take any element h and k belonging to the Cartan subalgebra, then this B of hk is the same as now this factor of 2. Okay, I mean I will just write it as that. I mean alpha h, alpha k, summed over alpha belonging to delta. This factor of 2, I think there are various places in these notes there are typos. Because if you write the sum over all the roots, then there is no factor of 2. Of course, you can rewrite this as 2 alpha belonging to positive roots. So you don't count alpha and minus alpha as two different roots. No? In that case, of course, you get a factor of 2. But at the moment, we have not even defined what's a positive root. I mean, for SU3, we know we have defined positive and negative roots. But generically, we have not defined that. Right? So let's just use this for part here. Okay. The summing over all roots. Okay. Well, we have proven actually, no, at least we have proven that for every alpha, minus alpha exists. So we can also still put a factor of 2, saying that we will not count alpha and minus alpha separately. That we could still do. So if you do that, and now let's use this formula, which is we have already obtained 2bh alpha h beta divided by bh alpha h alpha is equal to some integer. We'll choose p minus q, but let me just give it a name, n alpha beta, right? Because anyway, these integers will depend on alpha and beta, right? Which alpha you are choosing, which beta you are choosing, and also ordering is important here. Because this was alpha string through beta. If it's beta string through alpha, numerator is the same, but here it will become beta beta. No? So in this notation, the first index here is the alpha string through beta. So there is these two indices are not in the same footing. But anyway, we won't need all these details. The main thing is that this is an integer. That is what we need through beta. Okay. So this is of course the integer. That's the most important point here. This belongs to the integer. Okay. This is it. Now bh alpha h alpha. Let's compute that, right? Because if I want to show its positive definite, etc. I will, since I can expand any h in terms of h alphas, so let's first look at what is the bh alpha h alpha. So bh alpha h alpha, by using this formula, is simply, I shouldn't use this is the dummy index, right? Here I have put in alpha, so I should use some other symbol, let's call it beta. Beta belong to delta, or beta h alpha, beta h alpha. Okay. So that's the same as if I use this formula here, bh alpha beta is n alpha beta divided by 2 times bh alpha h alpha, right? So you get here n alpha beta. So this quantity is nothing else but b of h alpha h beta. Right? So it's a bh alpha h beta square. Right? So I take this. So this will become n alpha beta square, and then there's a factor of 4, and b h alpha square summed over beta belonging to delta. Is that correct? Yeah. I just put this here, divide by 2, and take the square. And then you get that here. So we have a nice relation. bh alpha h alpha is equal to this times square. Right? So this implies that bh alpha h alpha, I mean, we have already proven that bh alpha h alpha is not 0 in the previous theorem, right? So I can divide by bh alpha h alpha. So this is nothing else but 1 divided by sum over n alpha beta square over 4. Beta, 4 I can take up. So this is interesting, right? It's not only it's not 0, but it's a see, it's a rational number. It's a positive and rational number. Huh? So this is positive, and in fact, even more than that, it's a rational number. It's not just any real number. It's a rational number. So in particular, of course, it's a real number also, but it's very important. It's a rational also. Okay. Once we have done that, then I can get from this equation. From this equation again, we get BH alpha H beta is equal to BH alpha alpha divided by 2, so it gets 2 over sum n alpha beta square. Sorry, let me put here gamma now, because I shouldn't use the same dummy, because here there is a beta, right? I mean, maybe I should just change it, so gamma. This is a dummy index, right? I'm summing over all gamma. So n alpha gamma square. And then n alpha beta, right? N alpha beta. Now, so what does it tell you? That the Kaplan-Killing form, so between H alpha is a positive rational number. B of H alpha with any other root H beta is okay. It's not necessarily positive because n alpha beta could be negative, right? But nevertheless, it's a real number. Again, a real. So this is a real rational number again. That's so now so let's see. So this is fine. This is for just the roots, right? But we want to check for the entire HR. So the HR, what we call R, was this just restricted to real numbers, right? To real numbers. So this was the element of the HR. So what our aim was to show that this space is positive definite. On this space, the Kaplan-Killing form is positive definite. So far, we have just looked at the H alphas and H alpha, BH alpha H alpha and BH alpha H beta. These two things we know they are real. This is positive definite and that is real. In fact, rational numbers. But we want to do it for any H, right? So if you look at first of all B of HK, what I can say, because anyway H and K I can expand in like that, right? These are all real. So this, at the end of the day, once I have expanded that, it will be some R alpha, say H is that and K is some S alpha H alpha. No? Then it will become R alpha S beta, some B of H alpha H beta. Sum, right? Sum over all alpha and beta. But these are real. And those are anyway, again, real. So this whole thing is real. And so if you're expanding an element H and K in terms of H alphas, but with real coefficients. Of course, if R alpha, S alpha are complex, it will not be, right? But if it's real, then this is real. Right? So first conclusion is immediately that if for any H and K belonging to this HR, B of HK is real. Not complex. Okay, and then of course we can use the okay. So now let's take any H in here. There must exist some say beta belonging to gamma, belonging to delta, such that B of H beta. So in other words, so such that beta of H is not equal to 0. Right? This I think already follows from the fact that betas, alphas, the roots span the dual space. Right? This I think we have again used it before when we so then we can look. But what is that? This means it's B of H beta. I mean this quantity is nothing else but B of H beta H. Right? So this is not 0. Then I can now take B of HH, and that is, of course, by definition, that is that thing. So which is B of HH is alpha, or say gamma H square, gamma belonging to delta. But each of them is real. I mean, you see, this is sum. This is the same as B of H gamma square, right? Gamma belonging to delta. Is that, I mean, so we said this is in general true, right? So long as I'm taking real coefficients, this is general true, that this is real. Right? In particular, if I just choose K to be one of the H gammas, right? Which means just take the coefficients, all the other coefficients 0 except the gamma, make it 1. No? So that's a particular case. So we are saying that each of these terms is real. Each of these terms is real. Real square is always going to be positive, right? So whatever this is positive. I mean 0 or positive, right? Cannot be negative. But it's not 0 because certainly we said that there exists some beta such that BH beta H is not 0. So this sum, I can write it as, take that beta, so I separate out. So this is the same as B of H beta square plus all the remaining ones. All the remaining ones where we have B H gamma square, where gamma belongs to delta, but gamma is not equal to beta. So I'm just separating out this, just take out the beta part. But this is already, this is certainly not 0. I mean, we have chosen beta such that it's not 0. It's a real number. So this is certainly not 0, positive. And these are non-negative. So the conclusion is that BHH is positive. Except, of course, if H itself is 0. You could choose H equal to 0, right? But the moment H is not 0, BHH is not 0. It's positive, strictly positive. So that basically completes the proof that this in HR is positive definite. So B restricted to HR is positive definite. Is positive definite.
But just prove that B of H with H is positive definite.
Yeah.
But we didn't prove that B of H with K is positive.
Oh no, they will not be positive.
It will not be
No, it will be some real number, like any usual vector space, right?
No.
You can, the dot product can be negative, depending on the angles.
That a vector, a Cartan element dot with itself, it will be positive.
That's right.
But it's generally not true for all of them.
Sure.
But they will be real.
They will be real. Yeah. The real part we already proved previously. I mean, because these are already real. So since any H can be expanded like that with real coefficients, it's going to be real.
I think we can say that the norm of a Cartan element, it will be positive.
That's right. Yeah, that's right. So it's exactly like that's what I'm saying. We can now think in terms of Euclidean geometry. You know? So these alphas and betas, etc., are vectors, right? And their norms will be positive definite. The dot product can be negative depending on the angles between the two. No? Okay, maybe I will get back to this last part a bit later. the third 12.4 section. If there is no question, I mean, then so what I will do is I will maybe do the 12.4 tomorrow, because this is kind of a breaking from this main argument. I mean, this anyway. That's 12.4 is related to the fact that you see in the definition of the B. For the B, we said B we use adjoint. I mean, B was B of anything x with y. We defined it as a trace in the adjoint representation of x adjoint of y, right? Adjoint. So this is in a particular representation. We took the trace. But you can ask the question, what happens if I had chosen some other representation, right? Would it be the same, I mean, or is there some relation, or would I get totally different results? Okay. And that turns out the essence of the 12.4 is that if the algebra is simple algebra, not semi-simple, simple algebra, which means it has no ideal, no abelian or non-abelian ideal. Huh? So in that case, this will be proportional to, so if it is simple, so for simple algebras, this will be proportional to taking trace over any irreducible representation R. R is some irreducible representation. Actually, in fact, for any of them. Let's restrict to irreducible. Right? R of x, R1. It is proportional. In other words, what it is, this is equal to some number, C. That number depends, of course, on the representation R. So this number will depend on R, which representation I am choosing, but it will not depend on x and y. So the metric basically is proportional to each other. The metric you use to calculate using the adjoint representation or any representation. So for example, in the fundamental representation, we just compute in the fundamental representation. That's easier, right? Because that's a defining representation.
So is this number different for every representation?
Yeah, those numbers will be different in general.
So can we label that representation by
Sure,
this
yeah.
number?
Actually, that number plays a very important role in the anomalies and so on.
So we can,
That's the index of the representation.
So we can label that representation by this number only.
I don't know if you can. No, I don't think so. Because
So
there may be more than more than one representation which give the same number.
they are not different for every.
No, it's not.
This is always real, or it will be complex?
No, it will be real.
Positive? Positive?
Yeah, I mean, okay, CR is positive.
Because if it's positively definite.
No, I mean, so the point is that this is positive definite, you already saw, right? If you restrict to the, I mean, positive definite in the Cartan subspace. This is for the full Lie algebra. Now I'm talking about not just the Cartan, but also the, non-zero roots and so on. If you restrict to the Cartan, it is going to be positive definite. Okay. So this is also going to have this, since it doesn't depend on x and y, I mean, CR, from what I remember, CR is positive. But even if it is negative, it's an overall number. I'm saying it's an overall number. So the ratios are going to be, if you take the ratio, a ratio of two guys, then CR cancels. And if you take BXY divided by, say, B something else, say ZW, then those ratios cancel.
You said that it has an important role. How is that?
Which one has an important role?
The constants.
The constant plays an important role when you go through the anomaly calculations and so on. The coefficients really depend on this kind of quantities, index. Yeah. I mean, but that unfortunately, I think in this year you are not going to study anomalies at all. No.
In Diploma program, I don't think they're teaching anomalies at all.
No, because there's no time. I mean, quantum field theory, by the time you finish with the renormalization group, running coupling constant and so on, there no time is left over to discuss anomalies.
You're talking about QFT anomalies?
QFT, quantum field theory anomalies, yeah. But I mean, these numbers do play a role in various computations. Yeah, so I mean, because of this, it becomes quite easy. You can just directly compute it in the fundamental representation, which is the defining representation, right? So remember, for SU3 we had all these lambda matrices, right? You could directly compute it as a 3 by 3 matrix, because if in the fundamental for SU3 this will be 3 by 3 matrices, so you can compute all the metric there. Adjoint will be more complicated because first of all you have to construct 8 by 8 representations, no? So each of those lambda matrices, adjoint representation will be some 8 by 8 matrix. So to construct that and then compute, it's a lot of work, right? Whereas this one is much easier to calculate in the fundamental. Okay, so this, there's proof of this statement that this is proportional to that. I will postpone it depending on whether we still have some time left, because now there's 2 more lectures to go, right? Now the remaining time, what I will do is I will start the discussion about from the 13th chapter. Yeah, 13th chapter. No, not 13. 13 again we'll postpone for it later. 13 is a chapter I was mentioning that perhaps you can just read, because there are no concepts. I mean, it is just working it out for all the groups that you already, all the Lie algebras we already know, classical Lie algebras, no? SUN, SON, and SPN. All of this, unitary, special unitary, special orthogonal, and symplectic. For all of these cases, what this chapter 13 does is to construct all the roots, all the non-zero roots, Kaplan subalgebra, non-zero roots. So this is the main thing that is done here. So it is just but I mean, if there is time, I will come back to that in the last lecture. But today, let me just proceed with the general discussion, because at the moment we are doing a very general discussion. Because there are a few more things one has to say in the general discussion, and then one can perhaps go back to the examples. Okay.
And the problem from Friday?
Oh, so a problem. So how far you have submitted already?
Yeah.
Which up to which chapter? Up to chapter 10. Huh? Chapter 10. Oh, chapter 10 already you've done. Okay. So, yeah, I mean the 11. Yeah, 11, particularly that exercise 11.2 is very important, because that we keep using it. We kept using it many, many times. So it's chapter 11 and chapter 12. Are there exercises chapter 12? Yeah, there are a few exercises, not too many. Chapter 12. Okay, in this uniqueness of kata, there is no exercise anyway. So yeah, 11, 12. And 13 we said we'll postpone. But anyway, what I was suggesting was, I mean, if I don't get time, you should certainly go through chapter 13. There's nothing complicated about it. It is just kind of boring details. It's, you have to work out for each type of, like antisymmetric matrices for SON. You want to find what are the non-zero roots. What is the convenient choice of this? Like SU3, we chose a very convenient, Kaplan subalgebra, which was just a diagonal. It need not have been. You could have chosen something else, which would have made the calculations more difficult. But when you do just the diagonal guys, in a SO orthogonal, you cannot choose diagonal ones because it's by definition antisymmetric, the algebra. So the next best you can do is to choose, okay, I don't know, yeah, I mean, I'm just saying that, so the next best thing to do is to choose kind of, so you have this matrix, so choose, take SO2n, for example, say even number. Then what you can do is you can write 2 by 2 blocks. So write everything as a 2 by 2 blocks. So these are, each of them is a 2 by 2 block. So there will be n blocks here, n blocks there. Then since it's antisymmetric, so what you can do is you can choose, for example, 0, 1, minus 1, 0 here, right? And everything else 0. Or this matrix here and everything else 0 and so on and so forth, right? So that you will already find n of such matrices, right? Because there are n blocks. That will provide the Cartman algebra. Okay. It's a convenient Cartman. You cannot choose diagonal because there's no diagonal here. But the next best thing you can do is this. So in this 2 by 2 blocks is a diagonal block. Diagonal elements. And then you find all the other eigenstates and so on. So it's so case by case, you know. If it is odd guy, then after doing this n by n block, there is one element which is sort of left over. So these are all 2 by 2 blocks, right? But here there will be one left over. That leftover thing you cannot do anything. I mean, this has to be 0 anyway. It's a 1 by 1 matrix, and antisymmetric means it is 0. So the rank of SO2n plus 1 and SO2n is the same. It's not different. Rank. So SO2n plus 1 rank. Rank is the dimension of the Cartman algebra, right? This is the same as rank of SO2n. So there is a kind of distinction between the odd and even. All the even guys fall into one pattern. For any n, SO2n, they all fall into one pattern. SO2n plus 1 is slightly more complicated than that. I mean, they fall into a different pattern. That's a peculiarity. And the same thing, the SPN is not antisymmetric, but it satisfies those conditions, right? That omega, it's actually symmetric if you multiply by omega. Right? So again, there are some convenient bases and then work out the roots. So this is the main thing about the chapter 13. So try to read it, and if I do get time, I'll of course go through it, but I'm not sure. Yeah. So what I wanted to do, where is that chapter 13? Yeah, here it is. 14. Okay. So already lots of amazing things have happened. That these are all, I mean, not only real, but they are even rational numbers. It's kind of nice patterns. Let's continue. So I'm looking at chapter 14. Chapter 14. Okay, I will just start the discussion, and then of course I cannot be able to complete everything. So we have already used that definition, n alpha beta. N alpha beta was p minus q, right? So remember it was what? It was n alpha beta was by 2. And I will now kind of use the shorthand notation. Instead of writing always b h alpha h beta, I will just write alpha beta. Right? This is a shorthand notation. So, I mean, this was in fact, remember that we did obtain that. I mean, this was the B was the metric in the Cartan subspace, but then we could lift it to the metric in the dual space, because this alpha and beta are in the dual space, right? So that we already defined that at one point, this notation. So, but anyway, shorthand notation, let's say. So this is 2 alpha beta divided by alpha. And that is p minus q, where the string was from beta, this was alpha string through beta, and it started from beta minus p alpha and went up to beta plus q alpha. Yes, that was the string. So let's now, so there will be some integers. I mean, for each such thing it will be. So again, I emphasize that this is not symmetric in alpha and beta, as is explicit from here. I mean, the numerator is symmetric, but if I exchange beta and alpha, denominator will become beta beta. So it's not. So let's compute n alpha beta, multiply n alpha beta with n beta alpha. N beta alpha. So what am I going to get? It will be 4 alpha beta square divided by alpha alpha beta beta. Now what is this? I mean, you see, since we know that now we can think in terms of Euclidean geometry, right? So alpha and beta are some vectors, no? So this is alpha dot beta, right? And this is alpha dot alpha, the norm square of alpha, norm square of beta. So this is alpha dot beta. So this is what? This will be 4 alpha mod square, beta mod square. Mod, by this I mean this alpha alpha. And then cosine of theta alpha beta. So this notation is the angle between alpha and beta. Theta alpha beta square, right? Divided by alpha square beta square. Okay, so which is the same as 4 cos square theta alpha beta. Okay. So amazing thing is that this is an integer because the left hand side is integer. But this is also telling you, giving you a very strong restriction on the n alpha beta and beta alpha, right? Because we know that this is always going to be less than or equal to 1, right? So this product must be bounded by 4. No? So what are the possibilities? So n alpha beta. So we are saying that n alpha beta times n beta alpha has to be, now this is positive, so the only possible values are 0, 1, 2, 3 and 4. That's it, right? Because this is cos square theta, so they're positive. So, and it has to be integer, so it has to be 0, 1, 2, 3 or 4. They're the only possibilities. Now, when it is 4, so 2 of the cases are trivial. If it is 4, that means the theta is either 0 or pi. That means alpha and beta are not independent, they are in the same direction. So when this number is 4, then it just means that beta equal to plus alpha or minus alpha. Plus or minus alpha. So 0, angle 0 or pi. So nothing changes. Because as we have seen already, that if alpha is a root, then any number times alpha is not a root, apart from c equal to plus or minus 1. Right? So if the two roots are in the same line, right, the beta has to be plus or minus alpha. Okay. So this is a trivial case, so we don't consider that, because then it's not interesting, we don't learn anything from that. The same thing with the 0. 0 just tells you that they are orthogonal. Okay. So we can't again learn too much from that, from this statement. The interesting things are the other things, 1, 2, 3. So there is a, so we can, yeah. So we can see this table, which is in the 14.1. Now what are the possibilities? If I take 1, 2 or 3, these are all prime numbers, right? And I have to factorize this in terms of a product of 2 integers. So one of the integers must be plus or minus 1, right? No? Prime numbers, prime. I have to multiply, I have to write these prime numbers as a product. So I'm ignoring this also 0, not the, they are not orthogonal.
1 is not prime. 1 is not prime.
No, but I mean, if I want to write any prime number as a product of 2 integers, then one of them has to be 1, right?
But then you can multiply with 100 times.
No, I'm saying this is the formula, right? That this product is equal to 1, 2 or 3. Now I want to find out how I can realize it. What are the possible values, right? So at least one of them has to be 1.
Yeah, okay.
Or plus or minus 1, right? There is no other possibility. So we can choose our convention. In this table, one has chosen the convention that n beta alpha. We have chosen the convention that n beta alpha is plus or minus 1. It doesn't matter. If it was other, then you just rename what you call alpha and beta. It's not important. Huh? Okay. Then, so the possibilities are, n alpha, so n alpha beta, n beta alpha. Okay, we put the tables here. So if I choose 1 here, Well, n alpha beta can be anything between 1, 2, and 3, right? So I can have 1 here, okay. I can have -1 here, but then this also is going to be -1 because the product is positive, right? So whatever the sign is here, it should be the same sign there because product is positive. Then you can have again 1, but I can have 2, -1, -2, or 1, 3, -1, -3. These are the only possibilities. Okay. Now again, if I look at this expression, n alpha beta, definition of n alpha beta, which is 2 alpha beta from alpha alpha, this is positive, right? If this is negative, that means the angle is obtuse angle. Angle between the two is greater than 90 degrees, right? Between 90 and 180. Because cosine is negative, right? For between pi and pi by 2 and pi is negative. So if it is negative, then it should be obtuse angle, and if it is positive, it should be acute angle, right? So in this case, you see the angle between the, so theta alpha beta. In this case, so it is 1. So this is 1, and yeah, one more information. So if I take the ratio now, n alpha beta divided by n beta alpha. So in that case, what's going to happen? This will cancel, and you are left with the ratio of the lengths, but it comes in the opposite way, right? So alpha beta, so this will be beta square divided by alpha square. So for this case, it's clear that the lengths are the same. So in this case, alpha square, beta square equal to alpha square. In these two cases, because the sign anyway cancels from the ratio. In these two cases, n alpha beta is 2, so beta square is 2 alpha square, and in these two cases, beta square equal to 3 alpha square. So that's again just a basic picture. And now I can, since this quantity is nothing else but 2 alpha beta over alpha alpha, so which means it's beta divided by alpha, cosine theta alpha beta, right? I mean this is alpha dot beta, which is simply a length of alpha, length of beta times cosine, right? And here denominator is length of alpha square, so that's that. So in this case, since I substitute beta equal to alpha, this cancels, and you just get directly the information 2 cosine theta alpha beta. So since n alpha beta is 1, so cosine theta alpha beta is half, right? And half, what is the angle? 60 degrees, right? So this is 60 degrees. Yep. Whereas here, it is just as minus, so it will become minus half, which will be 120 degrees. These are exactly the angles we had for the SU3, right? In SU3, all the roots had the same length, and the angle between alpha 1 and alpha 3 was 60, and between alpha 1 and alpha 2 was 120. Now, if you look at this here, so this in this case, what we are saying, so n alpha beta is 2, so 2 cancels, but beta is square root of 2 times alpha, right? I mean, this implies beta is root 2 times alpha. So substitute that. So n alpha beta in this case is equal to 2, and then so n alpha beta is anyway we chose it to be 2. So 2 equal to 2, and then beta by alpha is root 2, right? Times cosine theta alpha beta. So 2 cancels, and you're left with 1 over root 2. So that's 45 degrees, right? In the 2. And this is just a minus, so 135 degrees. And when you have 3, so in this case we have a root 3. So so that thing will become 3 equal to 2 root 3 times cosine theta alpha beta. So this is root 3 by 2, right? So cosine theta alpha beta, I mean here it goes 1 over root 2, and here this is cosine theta alpha beta is root 3 by 2, which is 30 degrees. 30 degrees and 150 degrees. I mean this is 180 minus 30. So that's it. This is all the possibilities for the given 92 roots. But it's actually a little bit more restrictive than this, because here we just took one pair, alpha and beta, right? Now these numbers have to do with the lengths of the strings, right? So in principle, I mean, if let's say, say suppose beta plus alpha is also, or beta plus 2 alpha, for example, is also a root, then these statements must also, because this is for any pair of, right? So call this as some beta prime, right? Then the statement is that n beta, this n alpha beta prime, n beta prime alpha should also be between 0, 1, 2, 3. I mean 4. These are the only allowed values, right? So this has to be true with every pair, right? So that puts a restriction, and maybe I should just stop here. Let me see, just the last proposition I can say. So you could, right, the one thing you can arrive at, that the P plus Q, I mean here is information about P minus Q, that P plus Q is bounded by 3. So this was remember P minus, but the statement is that P plus Q, the next proposition is that, which is that P plus Q can be only between 0, P plus Q. I mean, there's certainly a positive number, I mean non-negative number, right? The way we have defined these guys, P and Q. So there's certainly non-negative, so it's greater than or equal to 0 and less than or equal to 3. Okay. And that is easy to show because that's okay. That's very easy to show because I mean start from this. So we have this, right? Take the beta prime plus Q. So call beta prime equal to beta plus Q alpha. Okay, so the highest one. So the highest weight state. I mean, this is an SU2 representation, right? The alpha string means is an SU2 representation, where SU2 being the X alpha, X minus alpha, H alpha, right? Because X alpha moves it, X alpha, X minus alpha move you across here, right? The representation. And this will be the highest weight. No? The highest weight. So we take the highest weight and call that beta prime. Then use this formula. So what will happen for the beta prime and alpha beta prime will be I mean, okay, what I'm saying is that this number now, so what is the chain now? What is the alpha string through beta? So consider alpha string through beta prime. Well, it will start with the beta prime is the highest, right? There. So then it can only go down, beta prime minus alpha, all the way up to beta prime minus P plus Q alpha, right? Because beta prime is simply beta plus Q alpha, just we're writing it in terms of beta prime. Okay. So this is going to be the thing. And now if I compute n beta prime alpha, or alpha beta prime, let's say alpha beta prime, then it's going to be 2 alpha, I mean that quantity, but what will be? It will be the new P prime and Q prime, right? For this chain, for this string. Okay. But here Q prime is 0 because the beta primes have, but P prime is P plus Q. Okay. So this is the same as P plus Q. Okay. And what we are saying is that this quantity also will be bounded by 3. Right? N alpha beta prime will be also bounded by 3. So that means P plus Q is bounded by 3. Is bounded by 3. So that was a claim that P plus Q is bounded by 3. So any chain, any string, you see can have maximum 4 elements, right? Because I mean, if P plus Q is 3, maximum 3, then you have beta prime all the way up to beta prime minus 3 alpha. So only 4 points will be there in that maximum. No? That's, so there are a huge amount of restriction, which of course means 4 points would mean what? Spin 3/2 representation of SU2. Right? Yeah. If there were 2 points, if this is 3, then we have a spin 3/2 representation. If it is 2, you have spin 1 representation. Of every time I'm talking about this SU2 subalgebra, alpha, SU2 subalgebra coming from alpha root. Right? So, and when this is 1, then it's a doublet, spin half representation. When it is 0, it's 0. That is a singlet. But this already tells you the maximum you can get is a spin 3/2 representation. Okay, so maybe I'll stop now and continue. Yeah, the next step will be to, just like what we did for SU3, we define positive roots, we define then the simple roots. So how can we do that in general now? I mean, so tomorrow we meet at 11.